Hi guys, today we are going to see some examples of this chapter 13 kinetic theory of gases. Let us start from example 13.1. The density of water is 1000 kilogram per meter cube. The density of water vapor at 100 degrees Celsius and 1 atmospheric pressure is zero point 0.6 kilogram per meter cube. The volume of a molecule multiplied by the total number of that molecule gives us what is called as molecular volume. Molecular volume is what? Number of molecule multiplied by volume of one molecule. Estimate the ratio or say fraction of the molecular volume and the total volume occupied by the water vapor under the above condition of the given temperature and pressure. So, what we need to find out is the ratio of molecular volume to the total volume of water vapor. Mind well, it is about water vapor. Alright. And what the given things are? The given things are the density of water and the density of vapor at 100 degrees Celsius temperature and 1 atmospheric pressure. Let us do this. First of all, I would like to explain something by this figure. See, the first figure shows the gaseous form, second one is showing the liquid form, and third one is showing the solid form. Here you can see that in solid and liquid, the molecules are very close to each other. Means we can consider like there is almost no space between the molecules, right? But in case of gas, the distance between molecules is quite larger compared to liquid and solids, right? So, when we talk about molecular volume, then molecular volume means the concentrated volume of this molecule itself, means the total volume of all the molecules without considering the space between is the molecular volume. Now it's simple to calculate this molecular volume by calculating the volume of liquid or say volume of solid, because in solid and liquid the molecules are very close to each other. So, the molecular volume will be equal to the volume of this solid or liquid. Now, here we have been given a case of vapor and water, right? So, in this case, the total volume what we are discussing is the volume of this vapor and can be represented as V. So, V is the total volume occupied by water vapor, right? Now, when we are talking about the molecular volume, then the volume of this much water is the volume of all the molecules. That means it is molecular volume, let us say Vm, because here all the molecules are very close to each other. So, this volume of liquid can be considered as the molecular volume of these molecules, and that is Vm. I am just noting it down. V is total volume occupied by the water vapor and Vm is the molecular volume. Now, the ratio that we need is of molecular volume Vm and total volume occupied by the vapor V. Now, because volume is mass upon density, so for Vm I can write m upon rho m, divide by for V I can write m upon rho. Mind well, here the mass will remain same. See, the mass of this liquid and the mass of the vapor formed from this liquid will be the same. So I am taking same mass m. Thus the equation will become rho upon rho m. Now here rho is the density of the water vapor and rho m is the density of molecules, or in other sense we can say it is density of water, because in case of water the molecules are very close. So the density of molecule will be almost equal to the density of water. So now we can find out the ratio of Vm upon V, and that will be equal to rho upon rho m, where rho is the density of vapor and which is given 0.6, and rho m is the density of molecules. But see, density of molecule will be equal to density of water, because in water all the molecules are very closely bound. That's why the density of water can be taken as density of H2O molecule, and that is 10 raised to 3. So we will get here 0.6 into 10 raised to minus 3. That means the ratio of volume that was asked of Vm upon V will be equal to 6 into 10 raised to minus 4, and this is our answer. Now let us see example 13.2. Estimate the volume of water molecule using the data in example 13.1. We have to estimate the volume of a water molecule using the data given in example 13.1. For that, we will start from the molecular mass of water, that means H2O molecule. Let us find out the molecular mass. Molecular mass can be denoted by capital M. Now here in H2O we are having two hydrogen atoms. So the atomic mass of two hydrogen atom can be written as 2, plus there is one oxygen atom. So atomic mass of this oxygen atom will be 16. So it is 2 plus 16, that means 18. 18 gram per mole is the molecular mass, or say molecular weight, of H2O molecule. Now this shows that 18 gram is the mass of 1 mole H2O molecules. So I can write which is the mass of 1 mole, that means 6.02 into 10 raised to 23 molecules. Thus the mass of one H2O molecule can be now written as, let us take M, then M will be equal to 18 gram, but it is gram, so I have to multiply it by 10 raised to minus 3, so it becomes 18 into 10 raised to minus 3 kilogram, divided by the total number of molecules, that is 6.02 into 10 raised to plus 23. So this gives the mass of one molecule, that will be nearly equal to, let us say, 3 into 10 raised to minus 26 kilogram. Remember, this is mass of one H2O molecule. So volume of one H2O molecule now can be written as, let us say, Vm. Then Vm will be equal to mass upon density, that is m upon rho m. Now mass of one H2O molecule is 3 into 10 raised to minus 26 kilogram. And the density of molecule, see, when we need density of molecule, that means we can take density of water, because in water all the molecules are very close to each other, so we can ignore the little space in between them, and so the density of water itself can be taken as density of H2O molecule, and the density of water is 10 raised to 3 kilogram per meter cube. So the volume of one molecule will become now 3 into 10 raised to minus 29 meter cube. This is our answer, that the volume of H2O molecule is 3 into 10 raised to minus 29 meter cube. Here we can also find out the radius of H2O molecule. Suppose the radius of H2O molecule is r, small r, okay. Now we can consider the molecule to be a sphere, and so the volume of this sphere, or say the volume of this molecule Vm, now can be written as 4 by 3 pi r cube, and this 4 by 3 pi r cube is 3 into 10 raised to minus 29, right? And now from this we can find out r cube. R cube is 0.717 into 10 raised to minus 29, or I can also write like 7.17 into 10 raised to minus 30. I am taking 10 raised to minus 30 purposefully so that I can take a cube root while finding the value r only. So now I can write that r is 7.17 into 10 raised to minus 30 raised to 1 by 3, and this will give us the value of R, that will be nearly equal to 2 into 10 raised to minus 10 meter, or you can also say it is 2 angstrom. 2 into 10 raised to minus 10 meter is 2 angstrom. So this is the radius of a 2 molecule, though it is not asked in this numerical, but this value will be useful for the next numerical. That radius of a 2 molecule is 2 angstrom. Now let us see example 13.3. What is the average distance between atoms, that means interatomic distance in water? Use the data given in example 13.1 and 13.2. Here it is said to find out the average distance between atoms, that means interatomic distance in water. I think there is a mistake here. It should be the distance between molecules, that means intermolecular distance, and not in water, it should be in vapor. So I will correct these things. We have to find out the average distance between molecules, that means intermolecular distance in vapor, because we are talking about H2O, that is molecule obviously, and second thing, in water we are considering all the molecules very close to each other. So we can take that distance, that means intermolecular distance in water, to be almost 0. But in vapor the distance between molecules is quite large. So here we need to find out the intermolecular distance in vapor using the data given in example 13.1 and 13.2. Now the ratio of total volume of vapor and molecular volume can be written as V upon Vm, and this V upon Vm from example 13.1 can be written as 1 upon 6 into 10 raised to minus 4. If you remember, in example 13.1 we have sought out basically Vm upon V, which was 6 into 10 raised to minus 4. So here we are finding V upon Vm, so it is 1 upon 6 into 10 raised to minus 4. That will answer us something 0.167 into 10 raised to 4. Means now I can write that V is 1.67 into 10 raised to 3 into Vm. Now here let me discuss something from this figure. See, the total volume of this gas is V, and the volume of all of these molecules, these are all molecules, so volume of all of these molecules is Vm, right? So this total volume V is 1.67 into 10 raised to 3 of Vm. Vm is the volume of all these molecules. Now see these green circles here. This green circle shows the volume occupied by one molecule. These are all the volume occupied by one molecule. See, every molecule is having some separation distance with other molecule. That means every molecule is occupying somewhat larger volume than their own volume. See, this is their own volume, and this is the volume which one molecule is occupying. So this green circles, rather I would say the green spheres, shows an imaginary sphere which is being occupied by every molecule. So if the volume occupied by this molecule is, let us say, V2, and the volume of the molecule itself is V1, and if the total number of molecules here are, let us say, capital N, then this V can be written as NV2 is equal to 1.67 into 10 raised to 3 multiplied by Vm can be written as NV1. Let me explain this. See, capital V is the total volume occupied by all the molecules. That means this total volume. So this total volume can be written as N times then V2. It can be written as N times then V2. And Vm is the molecular volume. That means it can be written as N times the volume of each molecule, that is V1. So Vm can be written as NV1. Alright. So here now this N will be obviously cancelled out. Remaining is V2. V2 is the volume occupied by one molecule. Now let us say the radius of this occupation is capital R and the radius of the molecule itself is small r. I repeat, the radius of the molecule itself is small r, but the radius of the spherical volume occupied by one molecule is capital R, right? So the volume V2 can be written as 4 by 3 pi capital R cube and volume V1 can be written as 4 by 3 pi small r cube. So I am putting that equation here. So we will get 4 by 3 pi capital R cube is equal to 1.67 into 10 raised to 3 multiplied by V1 is 4 by 3 pi small r cube. Obviously here too this 4 by 3 and pi will be cancelled out, and so we can get r. For taking r we have to take cube root of 1.67 into 10 raised to 3. So that I am going to put now, but before that let me create some space here. And so now I can write that r will be equal to 1.67 into 10 raised to 3 raised to 1 by 3 into small r. So from that now we can get the value of capital R. Here capital R will be nearly equal to 10 into small r. Now in example 13.2 we have derived small r. Small r was the radius of any molecule and that was 2 angstrom. So here it is 10 into 2 angstrom, that becomes 20 angstrom. So 20 angstrom is the radius of the spherical space occupied by one molecule. Now the final answer that we need is the intermolecular distance. Now see, intermolecular distance can be taken from center to center, means center of one molecule to center of another molecule, and that obviously you can see will be equal to 2r. So intermolecular distance will be 2r. So we can write intermolecular distance, let me name it like d, is 2 capital R, but if you take 2 into r, that will be 40 angstrom. So that is our final answer, that the intermolecular distance between two molecules is 40 angstrom. Now here is the answer, but now we can understand that this 40 angstrom distance cannot be interatomic distance. So the correction what I made is right. Interatomic distance cannot be 40 angstrom. Intermolecular distance can be 40 angstrom. Now let us see example 13.4. A vessel contains two non-reactive gases, neon, which is monoatomic, and oxygen, which is diatomic. The ratio of their partial pressure, remember this is partial pressure, is 3:2. Estimate the ratio of number of molecules and mass density of neon and oxygen in the vessel. Atomic mass of neon is given 20.2 AMU and molecular mass of oxygen is given 32 AMU. So here you have been given a mixture of two gases, both are non-reactive gases, neon and oxygen, and the ratio of their partial pressure is 3/2. Then we need to estimate the ratio of number of molecules and the ratio of mass density of both of these gases. First of all, assume that the volume of gas is V and the temperature is capital T. Now from the ideal gas equation for both of the gas, we can write the equation like P1V is equal to mu1 RT, and for the other gas we can write P2V is equal to mu2 RT. Obviously, as it is given here that P1 and P2 are partial pressure. So partial pressure means the pressure of the individual gas if it is taken in the same volume V and the same temperature T. That's why for the first gas we can write P1V is equal to mu1 RT, and for another we can write P2V is equal to mu2 RT. Obviously, here mu1 and mu2 are the mole number of both the gases. Now we can take ratio of these two equations. So we will get P1 upon P2 is equal to mu1 upon mu2. That means from this we can write mu1 upon mu2 is equal to P1 upon P2, but it is already given that P1 upon P2 is 3 by 2. That means here the ratio of mole number is 3 by 2. Now, as per the definition of mole, mole number mu is n upon Na, where n is the number of molecules and Na is the Avogadro number. So we can find out the first answer now. Now mu is equal to n upon Na. So the previous equation, let me call it like equation 1, that is mu1 upon mu2, can be written as this way: n1 upon Na, that is for mu1, upon n2 upon Na, that is for mu2, is equal to 3 by 2. So Na will be cancelled out and we can get n1 upon n2, that is equal to 3 by 2. So here is the first answer, that the ratio of number of molecules is 3 by 2. Now let us find out the second answer. Here again we will use one of the definition of mole number mu, and that is mu is equal to m upon capital M, where small m is the mass of gas and capital M is the molecular mass of the given gas. So now equation 1 can be written as this way: m1 upon capital M1, that is for mu1, upon small m2 upon capital M2, that is for mu2, and this value we already know that it is 3 by 2. So now we can write small m1 upon small m2 is equal to 3 by 2 into capital M1 upon capital M2. Now the ratio of density what we need to find is, let us say, rho 1 upon rho 2. So here rho 1 can be written as m1 upon volume V divided by m2 upon volume V. Here we are taking the same vessel, or say the same container, that's why both will have same volume V. Now this volume V will be cancelled out, remaining is m1 upon m2. So m1 upon m2 is 3 by 2 into m1 upon m2. Now capital M1 is 20.2 and capital M2 is 32. So this will give us the final answer, that is the ratio of density rho 1 upon rho 2, and that will be 0.947. So the ratio of density of both the gas is 0.947. That is our second answer. Alright. I hope you have understood all the numericals, and I hope that the figures that I am using to explain the question is helping you. Please give me some comments in the comment section about this. And as I always do, I have prepared a PDF of this whole lecture, and the link is shared in the description box. You can download the PDF from that link and can write the whole lecture, whole numericals from that PDF. Okay. So herewith signing off, Anshun Baldania.